Okay, a couple other ways that ICE diagrams might be presented and asked to be solved on the AP exam. The next is we've talked about given an equilibrium and given starting amounts of reactants and products, and one of the reactants or products pressures or concentrations at equilibrium. Using that one that's given at equilibrium to solve for the equilibriums of all the others. We just spent the last section was on that. How about if we're given the starting amount of reactants and none, and the K equilibrium value, and none of them at equilibrium? How do we solve for our equilibrium molarities or pressures? And very simply, there's a couple ways to do it. And the first way is perfect squares. If we look at our example here on example 1, notice it's giving us the synthesis reaction of hydrofluoric acid. Please note that it's given us a 1 liter container and 1.2 moles each of H2 and F2. And we divide by volume, moles by volume, to get molarity. It doesn't talk anything about having any HF, so that's going to start out as 0. And we know that if that's the case, this reaction is not at equilibrium. It needs to go forward. So our change will be minus x for each reactant because of the stoich, or the coefficients of 1. And it'll be plus 2x for HF because of the stoich, that coefficient of 2. And then to remember, I plus C gives us E, so I 1.2 minus x for each of the H2 and F2. And then just 0 plus 2x, or 2x for HF. Now normally, and they did give us our K equilibrium expression. So, and it's asking for what is the equilibrium amounts of each reactant and product. Well, the way we solve this is, well, two ways. You could end up using the quadratic, which you will I've never seen since the 70s using the quadratic equation to solve one of these. So one way they will give this to you so you don't have to use a quadratic is when we plug in our equilibrium values into our equilibrium expression. Notice we get 2x squared. We get 1.2 minus x, 1.2 minus x for each of the reactants. Now notice this ends up in the denominator being 1.2 minus x. And the top is 2x squared because of our equilibrium expression here. And we can then square root both sides, and that gives us a square root of 2.5, which is 1.58. And square root this will give us, on the right side, will give us square root of 2x squared is 2x. The square root of 1.2 minus x squared is 1.2 minus x. And then if we do our algebra here, and we bring the 1.2x over here, and we distribute, and we do our algebra and solve for x. Our x ends up being 0.53. Now, we could check our answer by plugging that x back in. So 1.2 minus 0.53. Again, at this point, it wants to know the equilibrium amount. So this will be 1.2 minus 0.53. And that'll be 0.67, 0.67, and this will be 2 times 0.53, or what is that, 1.06. Now we can check our answer by plugging these values back in over here, 1.06 squared, and then we can divide that by the 0.67 down into the bottom times 0.67. And when we do that, we get a nice value of 2.5. So we have just confirmed that these are equilibrium molarities of our reactants and products at equilibrium. Example down here at the bottom. Again, we're going to start out at 6 molar, and 3 molar. You then inject 15 moles of HCl, or remember, ICE diagram's got to be molarity or pressure, so that's 5 molar. So that means the equilibrium was initially 6, 6, and 3. By the way, when we plug that in, we get a K of 0.25 initially. Then we're going to plug in 15 moles of HCl into a 3-liter container. That's 5 molar HCl. So that means that this 3 molar goes up to 5 molar for a total of 8 molar. We know we just added product in, so we're no longer at equilibrium. We have too much product given this condition. So we're going to subtract 2x for stoic based on stoic and add x to each one as we go backwards. And bottom line is we're then going to go ahead and let's see. We got 8 minus 0.250 is 8 minus 2x squared. Again, that idea of perfect squares. And then on the bottom is 6 plus x squared. So square root both sides. We get our value. We get rid of these squareds. Do our solving. So at our change is 2 molar. So at our new equilibrium, that would be 6 plus 2, because that's the value of x. So that would be 8 molar. That would be 8 molar. And that would be 8 minus 2 times 2, or that would be 4 molar. Now we could quickly check our answer by plugging it back into our original expression over here. So that's going to be product, so 4 squared, if we plug it back into our original, divided by 8 times 8. And I believe if you plug that in, you will get a value of 0.250. So we have now checked that these are the new equilibrium values. All right. So let's go ahead and check, or on page 36 is a couple practices for these perfect square problems. And then finally, let's look at a type of problem where you are given a value of a very small k and large initial amounts of reactants or products. And there is a way to do these also without the use of the quadratic equation, although you could use a quadratic, but on the AP test, I've never seen them give you a problem where there isn't a way around that. Notice in our first example, we have the formation of nitrogen monoxide from its elements. So there's our, if you read this problem, it says our K value is 1 times 10 to the negative 5th. Notice that's very small, or we would say reactant favored. We know that because we have no nitrogen monoxide, that's 0 molar, so we know we have to go forward, so that's going to go up 2x. In each of these, we'll have to go down x because of the, again, the stoic of 1 to 1 to 2, again, minus 1 to 1, and then plus 2. Now, here's the key to doing these problems. You could set it up and solve this out, and you get a second-degree polynomial where you could use a quadratic. But the key to these problems is we're starting 0.8 and 0.2 molar is a rather large starting molarity. And because it is highly reactant favored because of this small value of equilibrium, we can assume that any amount that those two go down is negligible. And so we can essentially take an impact on our answer, and then we plug everything that's remaining in. So notice 1 times 10 to the negative 5th, and then we get 2x squared for the NO in our equilibrium expression, and then 0.8 and 0.2. Don't forget that when we do our algebra and we square this, we got to square both, distribute our squared, so that becomes 2 squared or 4, and that x becomes x squared. We do our algebra then, and our algebra gives us that x is 6.3 times 10 to the negative 4th. So what that's telling us is at equilibrium, this remains 0.8 and 0.2. If you don't believe me, go ahead and, using that as x, subtract that molarity change from 0.8 and 0.2, and you'll notice That'll pretty much, those two won't change. We can't, if we look over here, since we started with 0, even getting that little bit amount, that 2 times that, is a significant change from 0 molar, so we can't, that's not negligible. So we go 2 times 6.3 times 10 negative fourth. And so at equilibrium, notice our N2 and O2, what started out with significant amounts, is remaining the same. And then our NO, even that little bit that was made from this reactant favor, becomes significant because you started with none. Now, if you want to check your answer, you can plug these molarities back into this equation here. And when you do that, you will notice that you will still get 1 times 10 to the negative fifth for K. In our second example, so notice here we have NOCl in equilibrium going to NO and Cl2. Notice that our original K is very small. Remember, they always give temperature because equilibriums are temperature dependent. Please take a look that, notice we are not at equilibrium because we have 2 moles of NOCl in a 2-liter container. Don't let them trick you with that. Remember, in the NICE diagram, your amounts either are in molarity or in atmospheres. It started with 0 product. So we know we're not at equilibrium. We know the stoich is 2 to 2 to 1. So since we start with all reactant, that's got to go down 2x because of the stoich. And the products are going to go up 2x because of the stoich. And the chlorine's going to go up 1x because of the stoich. Now check this out. This is kind of cool. Notice 1 molar is a rather large starting amount. Because K is so small, remember K is really small, any amount that 1 molar changes is negligible. And so we can forget that change. We cannot forget either of these because they start out with no product. And so any even tiny amount of change is significant. And if we take a look here, we get, we set K equal to the equilibrium expression, then we plug in 2x for NO, we plug in x for Cl, and then 1 for the reactant, and we do our algebra. Remember, don't forget, when you have a square like this, you got to square the 2 and square the x. Do our algebra, and our algebra comes out essentially x is being 0.016. Remember, x is not the equilibrium molarities. That is just the change. So notice NOCl, even if you subtract 2 times this, is going to come out essentially 1 molar. The NO is 2x, so that would be 2 times 0.016 or 0.032. And at equilibrium, Cl2 would be 1 times 0.016 or 0.016. If you want to check your answer, go up and plug it in. Original equilibrium expression, those values, because they're supposed to be at the equilibrium, and they should come out, in this case, to 1.6 times 10 to the negative fifth, or your original equilibrium expression. Next example again, starting with all, looks like synthesis reaction. Or let's see, 0.5 molar of each reactant, no product, so we're not at equilibrium. We know that because we have each reactant, this has got to go down stoichiometrically to make the product because you can't ever have 0 at equilibrium. So minus 2x minus 1x. And since we had no product to start with, plus 2x. And notice, this is similar to the ones we've been doing, but now instead of starting with molarities, we're starting with pressures. And if you take a look, notice we get our 2x squared over 0.5. Remember, we call these negligible because K is so small that we can consider those are negligible. We solve for our value for x. Notice, even if you subtract those the 0.00187 atmospheres from the original 0.5. That does not change significantly, but we can't forget about the plus 2x here because we started with none of this. Now, if you take these values, equilibrium values, and plug them back into here, into our equilibrium expression. So if you take these values and plug them into here, you should get a value of 0.000056 molar. All right. And then let's take a look. K of 1.2 times 10 negative fourth, rather small k. And it says we start, catch it, solid, can't be part of the equilibrium expression. We start with no product, 0 and 0. And then we're going to get, it's got to go up stoichiometrically by x and x, go up by x and x. So when we solve for x, we get 0.0110 molar. Now we could easily check this out by plugging this value. So this happens to be 0.0110 molar because that's x at equilibrium, and this is also x at equilibrium. And if you were to plug those values back into here, you are checking your answer and get 1.2 times 10 to the negative fourth. And then finally, sometimes you'll see a problem like this. Notice we started out with 1 molar. So if we want to think of a little ice diagram here, we started here with 1 molar. And then at equilibrium, out here at this time, whatever that might be, we ended up at equilibrium of 0.80. So it went down 0.2. Now notice, it had to go down 2x to get to 0.8 because of the stoich. So this is going to be 0, 0. This is going to be plus x, plus x. Now, remember here, that's saying that 1 molar, and that's going to be minus 2x because of the stoich has to equal 0.8. So that means that if we take a look here, that we're going to get essentially minus 2x equals, subtract 1 for both sides, minus 0.2. So x is equal to what? 0.10. So that means this is going to go up. So x is equal to 0.10. So this is going to go up to 0.1, and this is going to go up to 0.1. So in both these cases, if we looked at equilibrium, the concentration of H2 and the concentration of I are both going to be 0.1 at equilibrium. And notice the 1 went down 2 of those to get us down to 0.8. So Kc expression is equal to, looks like H2 times I2 over HI squared. HE at equilibrium, HI at equilibrium would be where we get that plateau. So that would be 0.80 molar. Again, equilibrium, we kind of did it up above, and I'm going to draw your attention up here. We started with 1 molar at time 0, or initial, 0 of the H2 and I2, and we just solved for x and plugged that in. So for part C1, we did that up there at the top. Value of the equilibrium constant. So let's look at Kc. So Kc is equal to concentration of H2 times I2 over HI squared, and that's going to be 0.1 times 0.1 times 0.8 squared. Now that's going to be, let's see, 0.1 squared divided by 0.8 So I believe that's 0.0156 is our Kc. Now remember, Kp equals Kc RT delta N. And remember, N here would be products minus reactants. And notice we have 2 moles of product gases, if we add up the coefficients, minus 2 moles of reactants gases. So delta N is equal to 0. And so that equals, so notice here, so delta N is 0. So Kp equals Kc, which is equal to 0.0156. And then finally, if you notice on part D down here at the bottom, when we used our ice diagram, we were easily able to sketch in that. Now remember, kinetics-wise, we could have changed concentrations, we could have changed initial concentrations, we could have added a catalyst, we could have done many factors to get to our equilibrium expression more quickly. One thing we couldn't have done is change temperature, because that would have changed the equilibrium amounts, because remember, equilibrium or equilibria are affected by temperature. Last type of question is not seen real frequently, but determining an initial concentration from an equilibrium concentration value, or K equilibrium, and equilibrium concentrations. So take a look here. Methanol decomposing to hydrogen gas and carbon monoxide gas, our equilibrium expression. And then notice it says CO at equilibrium is 0.15. Now notice our stoich, that tells us that started at 0. So we started with some initial amount of methanol. At equilibrium we have 0.15. Using that, we can show that x, the amount this went up is 0.11x. So this had to go up 2x, or went up to 0.3. This had to be x minus, or starting amount minus 0.15. Because of the stoich. Remember, it's a stoich of 1 to 2 to 1. And what's really cool now is now we know our equilibrium values. Our only unknown in the equilibrium values are starting molarity of methanol. So when we plug this into our equilibrium expression, we know the value of K. We now, the only unknown is there, which is your starting CH3OH molarity. When we do our rearrange and solve, we can see that that started out with a molarity of 0.488. If you want to check your answer, plug that value in here, subtract 0.15, which would be, let's see, 0.488 minus 0.15. That would make this 0.338. This would be 0.3. This would be 0.15. Plug those in here, and to check your answer, you should plug those in, multiply it out, you should get 0.040, and I believe you do. So we're done now with all of equilibrium, the initial part, except for the last section, which is Le Chatelier's principle. If you'd work on now pages 41, or page 41, and that's it, which will help you practice that last type of problem we did. And then we will talk, the last section for this unit, for 12A, is Le Chatelier's, and I'll work on that in just a little bit. Good luck. Email me if you have any problems, and get to page 41, please. Thanks.